Yes, good morning, students. So today I will discuss Norton theorem. It is a theorem. It is a methodology with the help of which I will be able to calculate current, voltage drop, or power loss across any of the particular load resistance or a particular branch. Right? We had already discussed that Thevenin theorem. Now here again I am just selecting this R4 branch as a load resistance branch. R4 branch as a load resistance branch, right? So in this case again, first step is step 1, remove load resistance. Up to R7 steps are same. Only difference is instead of because there we are having that Thevenin theorem, I am just representing that with the help of RTH. Here I will just represent that as a Rn. Otherwise, that methodology that to calculate R equivalent or R Thevenin, that will remain same. So step 1 is remove the load resistance and redraw the circuit again. Remove the load resistance and redraw the circuit again. So after removing the resistance, I am here taking this R4 as a load resistance. So after removing it, this is your network, right? You may redraw it again. Then after that, step 2 is short circuit all the voltage sources. Short circuit all the ideal voltage sources and open circuit all the ideal current sources. Right. So here in this case there is only one voltage source, right? No current source is there. So I may remove it and short circuit may be applied. If in any case some internal resistance of the source is given, then replace that source with that equivalent internal resistance. Right? In 99% of the cases, no internal resistance of the source is given to you. Right? So that's why we are applying short circuit across the voltage sources and open circuit across the current sources. So after applying that second step, this is your network. Step 3, calculate R equivalent across load resistance terminal. Calculate R equivalent across load resistance terminal and that equivalent resistance is known as Norton equivalent resistance. Norton equivalent resistance, right? And it is denoted by Rn. So here I may calculate Rn, right? So Rn is same as that of the previous Thevenin theorem because I am just considering the same network, right? So Rn is equal to R1 in parallel with R2, and this combination is in series with R3, right? So here this will be R1 R2 divided by R1 plus R2 plus R3, right? So this will be the your value of R Norton in this particular case, right? Now after this, step 4, again place all the energy sources in the network. Again place all the energy sources in the network again, right? So this will be the circuit after applying step 4. Here we are having this voltage source, no other energy source is there, right? Now what to do? Step 5, you will have to, again I am repeating, you will have to redraw the circuit again after each step. I am just manipulating the circuit in the same, but you will have to redraw the circuit after each step. Fine. So step 5 is apply short circuit across load resistance terminal. Apply short circuit across load resistance terminal. So this is your load resistance terminal. Here I am applying the short circuit and calculating ISC, that is known as Norton equivalent current, right? Apply short circuit across the load resistance terminal. Here I am applying the short circuit. Next step is calculate short circuit current across the load resistance terminal. And it is known as I Norton, IN, Norton equivalent current, right? So this is known as IN, Norton equivalent current. Right. So here I will have to calculate ISC. In case of the Thevenin equivalent resistance, in case of the Thevenin theorem, we will have to calculate VOC, that is the open circuit voltage, and that is known as VTH, Thevenin voltage. Here, in case of the Norton theorem, we will have to apply the short circuit and calculate ISC, and that ISC is known as IN, right? Now for calculating IN, again I will have to use either KCL or KVL, both may be applicable here, right? So here let us say this is your node A. In this circuit, this is your node A. So I am just going to apply KCL, across node A, apply KCL across node A. So for that, I will have to assume some direction of the current. Let us say this is direction of the current I1, this is your direction of the current I2, and this is your direction of the current I3, and I3 is equal to ISC. I3 is equal to ISC, right? So as per the Kirchhoff's current law, as per Kirchhoff's current law, summation of I is equal to 0, right? Summation of I is equal to 0. Algebraic sum of all the currents meeting at a point is equal to 0, right? Or in other words, you may say that incoming current is taken as positive and outgoing current is taken as negative. Incoming current is taken as positive and outgoing current that is taken as negative, right? So here in this case, in this particular case, there is no incoming current because all are leaving this junction A. So that means at A, I1 plus I2 plus I3 that will be equal to 0 because there is no incoming current. All the currents are in the direction. So I1 plus I2 plus I3 that will be equal to 0, right? So let us say here we are having the voltage VA, right? Here we are having the voltage VA. So I1 is equal to VA minus V1 upon R1 plus VA upon R2 plus VA upon R3 that will be equal to 0, right? VA minus V1 upon R1, because what will happen that as per the Ohm's law, I'm just going to explain this how that equation will become. Because as per the Ohm's law, what will happen? Let us say this is your resistance. Here I am taking the potential VA. Here I am taking the potential VB, and I am assuming that VA is greater than VB. Right? VA is greater than VB. That means current will always flows from higher potential towards the lower potential. Right? So that means current will flows from VA towards VB. Fine. So as per the Ohm's law, I is equal to potential difference upon resistance. Right. So what is the potential difference here? VA minus VB. VA minus VB divided by R. Right. So potential at one terminal is VA, potential at the other terminal is VB. If this is the direction of the current, current will always flow from higher potential towards the lower potential. This is the nature of the current. Current will not follow from the lower potential towards the higher potential, right? So current will, if this is the direction of the current, that means VA will be greater than VB, right? So potential difference will be equal to VA minus VB upon R. As per the Ohm's law, current flowing through the network is directly proportional to the potential difference applied across it, right? So V upon R. So V is equal to potential difference. So now see, in this case, I'm taking this as the direction of the current. That means here I am assuming VA. So that means VA will be greater than, if you will see this resistance R1 across one terminal, of the R1, VA is connected, across another terminal, V1 is connected, right? So VA minus V1 upon R1. VA minus V1 upon R1. In second case, in this part here, there will be no potential. Here potential will be 0. So VA upon R2, VA upon R2. And in this case, again, at this node, your second terminal of the R3 is connected. And here again, potential is 0. So that's why I am taking I3 or ISC is equal to VA minus 0 upon R3 or VA upon R3. So this is the equation by applying KCL at node A. Now in this case, if you will see, there will be only one unknown, that will be VA. I am assuming the voltage VA across node A, right? So there is only one unknown in this equation. So because V1 may be 2 volt, 3 volt, 4 volt, whatsoever that value will be given to you, R1, R2, R3, all that values will be given to you, right? Only one unknown is there, and that will be VA. So by solving this equation, if some numerical will come, right? If some numerical will come, by solving this equation, you will be able to calculate VA. And by substituting VA I3 or ISC is equal to VA upon R3, you will be able to calculate short circuit current, right? So after calculating VA from equation 1, let us say this is your equation 1, value of the current ISC, that is the short circuit current, that is the Norton current, may be calculated by using ISC is equal to IN, that will be equal to VA upon R3. Right, in one of the step I had calculated Rn, and in this step I had calculated ISC or Norton current. Right. Now next step is, let us suppose the next step is step 6. Step 6, make Norton equivalent circuit. There we are making Thevenin equivalent circuit. So make Norton equivalent circuit and Norton equivalent circuit will consist of 3 elements. Which one? Rn, then In and RL. Right? Norton equivalent resistance, Norton current, and load resistance. Right? And all that elements in this case all 3 elements are connected in parallel. Right? In case of the Thevenin theorem, all 3 elements, which are that 3 elements, RTH, VTH and RL, that are connected in series. But here in case of the Norton theorem, all that elements, that is Rn, In and RL, that are connected in parallel. So this is your Norton equivalent network. IN, RN, and here it will be RL. So this is your Norton equivalent network. Norton equivalent network will consist of three elements: IN, RN, and RL, and all that three are connected in parallel. So I may calculate the current here, and that current is the load current, required load current. Next step, step 7. Step 7. So calculate load current IL by using current division method. By using current division method, right? So that is IL is equal to total current, that will be IN into opposite resistance RN divided by RN plus RL. So IL by the use of Norton theorem, IN is equal, IL is equal to IN into RN divided by RN plus RL, right? So in this equation, 2 are our calculated value, IN that will be calculated, and RN that will be the calculated, and RL is the load resistance which is removed in very first step, right? So this is your, this equation represent your value of the that load current by the use of Norton theorem. Now, if required, next step, step 8, if required, step 8, if required or asked, value of voltage drop or power loss across load resistance may be calculated by using the relation VL is equal to IL into RL, and power across the load that will be equal to IL square RL. By using these relation here, IL will be the value calculated from step 7, right? So this is all about the Norton theorem. Now, one thing that must be critically noted, that if you see the equivalent circuit of Norton and Thevenin, this is your Norton equivalent circuit, right? And if you see that Thevenin equivalent circuit, that will be, this is your VTX, here it will be RTX, and here it will be RL. So this is your figure, let us suppose 2, and this is your figure 1. Figure 1 gives you value that equivalent circuit of the Norton theorem, and figure 2 gives you value of the Thevenin equivalent circuit, right? And in this case, what will happen here, that if you will see, by comparing these two circuits, next I am taking as step 9. If you will see, by comparing circuit 1, figure 1 and figure 2, figure 1 and figure 2, what you will see, first of all, RTH is equal to RN, because I am taking the same network. If they are for the same network, then RTH must be equal to RN, right? Because we are using the same step and same value of the distances. I am just keeping this thing in mind. I am solving this circuit for the same network. If I am solving I am calculating the current for the same network, then I had applied the same step, remove the load resistance, short circuit all the voltage sources, open circuit all the current sources, right, and calculate the equivalent resistance across the load terminal, right? In both of the cases, either in case of the Thevenin theorem or in case of the Norton theorem, I had applied the same steps. So that means value of the RTH will be equal to RN. Value of the RTH will be equal to RN for the same network, right? So if you compare these two circuits, fine. This is I had already told you that source transformation, right? Source transformation, fine. By using source transformation, what will happen if, let us suppose, this is your VTH and this is your RTH, right? And if I will have to convert this into equivalent current source, then this will be the current source. Current source is having the value VTH upon RTH, right? And here this RTH will be in parallel, that will become RN, right? So VTH upon RTH, that is your value of the IN. VTH upon RTH, that is your value of the IN, and RN will be placed here in parallel. So that means both of that network are same. Both of that network are same, right? So by using the source transformation, it may be seen that both of the networks are same, right? So we may say that Thevenin theorem and Norton theorem so it may be concluded that Thevenin theorem and Norton theorem are dual of each other. dual of each other, right? We may say that this is the only different methodology, right? In both of the theorem, this is the only different methodology. Otherwise, at the end, we will get the same result. So they are not opposite to each other. It may be seen that both are dual of each other. Dual means like same. Only methodology is different. Otherwise, whether you will use that Thevenin theorem or you will use Norton theorem, if we are applying the theorem on the same network, then result will be totally same. So that means if in one case I am getting the current as 3.2 ampere, again in the second case I am getting the current as 3.1 ampere only, right? So this is all about the that Norton theorem. Now just take this example. This is the network. Calculate the current through 10 ohm resistance by using Thevenin theorem. That means here I will have to calculate. This is your RL here. Okay. In this case, this is your RL, because the question is by using Thevenin theorem, calculate the current in 10 ohm resistance. Right? We will follow the same steps and calculate that required value of the current. So step one, remove the load resistance. So here, first of all, this thing must be noted that RL is equal to 10 ohm, right? So remove the load resistance. After removing this is your network. Let us suppose this is your terminal A and this is your terminal B, right? Then step one is remove the load resistance. After removing this will be the network. Step two, here because again there is only voltage sources, no current sources there. So apply short circuit across voltage sources. So there are two sources. This is source one. So this may be short circuit, and here it will be the source two. So this will be again the short circuit, right? Now you will have to calculate step three. Calculate or Thevenin or equivalent across load resistance terminal. Fine. So here I will have to calculate RTH. So I'm just going to redraw the circuit by taking A and B at the outer terminal, right? So this is by practice. This is your terminal A and this is your terminal B. So starting from A, 15 ohm resistance, and second terminal of the 15 ohm resistance is connected at B, right? So this is here 15 ohm, right? Then after that, if you will see from A, again 5 ohm one terminal and second terminal is connected at B. This is only by practice. No other method is there. So here it will be 5 ohm. So 15 ohm and 5 ohm are in parallel. From this network, you may not be able to conclude what should be this connection. But from this, it will be very clear that 15 ohm and 5 ohm are in parallel. So RTH is equal to 1 upon RTH. R equivalent is equal to 1 upon RTH. That will be equal to 1 by 15 plus 1 by 5. Right? So 15 is the LCM. 1 plus 3. So 4 by 15 or R Thevenin, that will be equal to 15 by 4 ohm. R Thevenin for this circuit, that will be equal to 15 by 4 ohm. Right? Now next step is again place all the energy sources in the network. Step 4. Place all the energy sources in the network and calculate VOC or VTH across load resistance terminals. Right? So RTH and RL is equal to 10 ohm and RTH is equal to RTH is equal to 15 by 4 ohm. Right? So now I just place here one energy source is there and here second energy source is there. Right? One is of the value 50 volt and second is of the value 100 volt. And positive terminal of both is towards upward. So this is the network after placing all the energy source in the circuit. So just redraw this circuit, fine, to calculate VOC, that will be equal to VTH, right? VOC, that will be equal to VTH. So again, I am taking this A and B terminal outside. This is a terminal A and this is a terminal B here, 15 ohm and 100 volt. Okay, positive is towards the upward, towards A terminal. Then here it will be 5 ohm and 50 volt. So this is the network and here I will have to calculate VOC and that will be equal to VTH, right? So whatsoever voltage will be appear here, that will be the your VTH, because in this side there will be no element, fine. So here you may see this will be the closed loop. This is your closed loop, and in this closed loop I am taking this is the higher value voltage source, this is the lower value voltage source. Current will flow through in this direction, I, fine. So here I am applying KVL. By applying KVL, what you will get? That summation of V is equal to summation of IR. So 100 minus 50, that is equal to 50I plus 5I, because here positive both is connected with each other. One will be supplying in this direction and second will be applying in this direction. So that's why I am just subtracting these two voltages. If negative of the first is connected with positive of the second, then they will be added here. Fine. So this will be that 50 is equal to 20I. From this, I is equal to 50 upon 20, 2.5 ampere. Right? Current in this branch, that will be equal to that 2.5 ampere. Now here, this will be the direction, right? In this resistance, current entering in this, so here it will be positive and here it will be negative. Across 15 ohm resistance, lower terminal is positive because from which side current will entering, that will be taken as positive, and from where it will be leaving, that will be taken as negative, right? So in this case, let us suppose here voltage will be V15. Voltage across the 15 ohm resistance, that will be V15, right? So V voltage drop across 15 ohm resistance, that will be V15, that is equal to I into 15 ohm, I into R. I is calculated as 2.5 into 15, right? So here it will be 75, 37.75. B15, that will be equal to 37.5 volt, right? 15 into 2.5. 2.5 is the current in that loop, right? Now, because here, if you will see, positive of both will be connected with each other. So across this complete branch, VOC is equal to 100 minus V15, right? From circuit, VOC is equal to VTH, that will be equal to 100 minus voltage across the 15 ohm resistance. So that will be 100 minus 37.5. So this is equal to 61.5. VOC is equal to 61.5 volt. Or 62.5. I think this is 62.5. 62.5. Right? 100 minus 37.5. That will be 62.5. So VOC, that will be equal to 62.5 volt. So these are the three values for Thevenin equivalent circuit, right? So now next is make the Thevenin equivalent circuit. Next step, make Thevenin equivalent circuit. Thevenin equivalent circuit. It will consist of these three elements: RL, RTH, and VOC. VOC is equal to VTH, right? So here it will be VTH of the value 62.5 volt. Then 15 by 4 ohm, that is your value of the RTH, and here it will be RL, that is of the value 10 ohm, right? And I need current, so IL is equal to VTH divided by RTH plus RL, so that is equal to 62.5 divided by 15 by 4 plus 10. So you may calculate it. That is the value of the this load current. Just a minute, I am just going to calculate it. Fifteen by 4, that will be 3.75 plus 10, 13.75. So 62.5 divided by 13.75, right? 62.5 divided by 13.75. So that will be 4.54. So IL is equal to 4.54 ampere. Right. So this is the required answer. IL load current through the load resistance branch, that will be equal to 4.54. If you will take next, it will be again 5. 4.545 ampere. Right. So this is the end of the lecture. We will meet in next lecture again. Thank you.